learn as humans coming into this world. As seasons change, so did the temperature of our surroundings. And it didn't take long for scientists to determine that we needed a way to measure the difference between what's hot and what's cold, so the thermometer was created. Well, why call it a thermometer? Well, thermo comes from Latin meaning heat, and meter is to measure, so simply put, a thermometer is a way to measure heat. But you don't need to be Galileo to make a thermometer. Come on, I'll show you what I mean. To build a simple thermometer, you'll need a clear bottle, rubbing alcohol, modeling clay, food coloring, a clear straw, and some water. Start by filling your bottle with equal parts rubbing alcohol and water, so the container is about a quarter full. Add some food coloring so you can see the liquid better. Warning, do not drink this liquid. Wrap the modeling clay around the straw as so. The goal is to make a top for the bottle so the straw is suspended in the liquid but not touching the bottom. Seal the clay around the opening of the bottle so that no air may escape. Alright, we're done building the thermometer, now let's see if it works. Heat up some water on the stove so that steam just becomes visible, and take the thermometer and place it in the water. Watch what happens. Hey, it works! The alcohol solution is flowing up the straw as the thermometer heats up. It works the other way too. Take the thermometer and place it in a bowl of ice water. Notice the liquid in the straw starts to fall now. So why does this happen? Well, if you look back to the egg in the bottle view, the answer is the same. Expansion and contraction. As our alcohol solution heats up, it expands, forcing it to move up the straw. When it cools, the opposite happens. The fluid contracts and drops back down the straw again. So you may be wondering, why are we using alcohol in our solution? Why not just water? Well, two reasons. One, alcohol reacts more quickly to temperature changes than water, and it has a lower freezing point than water, allowing for measurement of temperatures below 32 degrees Fahrenheit. Yep, 98.6. Though nearly 400 years have passed since the creation of the thermometer, it's interesting to know that the principles behind it are effectively the same. What's true then is true now, and Galileo himself would likely agree that this is a great one of life's little mysteries. For Vudu.com, I'm Alan Puccinelli.
Okay, so your really basic thermometer works on these principles. May need more time? So we're going to talk about 3 temperature scales today, and mention one more, but talk about 3 of them. Now, there's lots of temperature scales. And remember, the thing about all of them, they all measure change in kinetic energy, no matter what we're talking about. But we're going to look at Fahrenheit, Celsius, and Kelvin. Celsius and Kelvin, because that's what we use in class, and Fahrenheit, because that's the one you guys see in the world around you. Fahrenheit. Fahrenheit was probably our first widely used scale, kind of the first worldwide kind of scale. And it was invented by David Gabriel Fahrenheit in Danzig, Germany in the early 1700s. We're not quite sure exactly when, but it's sometime in the early 1700s. Now, there's evidence that it was based on an earlier scale by Romer. Romer was an astronomer. We'll actually see him later on because he did some work with speed of light. He gave us gives the idea that speed of light is not instantaneous. It's not infinite. That it actually had a finite speed here. And by Newton. And it is associated with the Rankine scale. Rankine is an absolute scale. Like Kelvin is an absolute scale, Rankine is an absolute scale, but it associates with Fahrenheit, just like Kelvin and Celsius are associated. But Danzig in Germany, if you know anything about the geography of Germany, Danzig is a port city. It's on the Baltic. All Germany's ports are on the Baltic Sea. Anybody know what happens to the Baltic in the winter? Freezes. Now, so one thing he was concerned with was, when does it freeze? Because once it's frozen, you're stuck. You ain't going anywhere. You really want to get out. If you need to get out, you want to get out before it freezes. You want to be able to get all the way out, have enough time to get out before everything freezes. Obviously, you also want to know when it might not be frozen anymore. Because it's early 1700s. Might think, well, they get some of the icebreakers. Well, that's what they do now. You know, you big steel ship crunches through the ice. And they didn't have that then. There's no such thing as a wooden icebreaker. At least not a very good one. Believe it or not, they did build wooden icebreakers. They didn't work very well. But they are actually clad with metal. But, nowadays, big steel ships break ice. And back in these days, ice broke wooden ships. And a lot of Arctic explorers kind of met their fate that way. The ice kind of crushed the ship. So we kind of want to know things about that. And he was worried about that. Anyone need more time? So we'll start with a couple we might know. 32 degrees Fahrenheit. What happens at 32 degrees? Water. What kind of water? Pure water. Pure water. Fresh water. Pure water. Fresh water freezes. What happens at 212 degrees Fahrenheit? Steam. Well, what do we call that process? Steam is being produced. Starts with a B. Boiling. Although evaporation does do that, that's kind of a little different place. Boil. But fresh water boils. 0. Remember, what was he worried about? What low temperature thing was he worried about? What freezing? What kind of water? Salt water. Seawater. Seawater. So 0 degrees is where seawater freezes. This is where seawater freezes. 0 degrees. Because of the salt. This is why also when you throw salt on ice, what happens to it? It melts. We don't use it in California. In California, the roads, they put sand on the roads. They put sand on it. But most other places, they use salt. Except in Seattle, they started using sand. It doesn't work very well. Try Seattle. I don't know if you know, Seattle has hills like San Francisco, but they get ice on them. They don't salt them. They want to put sand on them, so it's like the fire department can't get up to the top of the hill. Police department can't. All because some salt might get into Puget Sound. Salt might run off in Puget Sound, which is salt water. 100 degrees. What do you think? Actually, salt water boils a little higher than 212. But let's hope the salt water doesn't boil at 100 degrees, because we'd be in a lot of trouble, wouldn't we? Body temperature, human temperature. It was Fahrenheit's intention that 100 degrees Fahrenheit would be our normal human body temperature. And maybe it was for him. 98.6 is the average. There's always those outliers. He might have been one of the extreme outliers. Maybe for him, 100 degrees was his body temperature on that. It's one of those things, you should really know what your body temperature is when you're well. You should, over several days, you should take your body temperature when you're not sick, so you know what your normal body temperature. Like for me, I know my body temperature normally is around 97.6. So if I have a 100 degree temperature, so if my temperature is 100 degrees, I'm actually kind of running a temperature. A pretty good temperature there. Even 99 degrees, I'm running basically about 1.5 degrees of a fever. Most people, 99 degrees, that's really nothing. That could be daily changes. But for me, that might mean I have just a very slight fever on that. So a good idea to know what your normal is. So these are the set points for Fahrenheit. Fahrenheit. First widely used system. We still use the United States. Even in English-speaking countries, you sometimes still see Fahrenheit in weather reports and stuff like that. Celsius. Anders Celsius. About 1740. So about 30, 40 years or so after Fahrenheit. it wasn't widely used at first, although it was kind of adopted into the metric system. It is not a metric unit. Obviously, it was not developed with the metric system. But originally it was called centigrade. Centigrade temperature. I mean, doesn't it look like, we think about the set points. We look at this, that 0 degrees is that fresh water freezes. And 100 degrees, fresh water boils. 0 to 100 kind of sounds like metric, doesn't it? Better than 32 and 212, right? But it sounds like the metric system. So when I was actually in middle school, we called it centigrade. Degree C, but I learned it as centigrade. It wasn't actually too long after they changed it to Celsius on that. So on that, by the time I got to college, it was Celsius and all that. But centigrade is how I first learned it back in the 70s. But the thing is, this is not our SI unit for temperature. Although we use it and can use it, and there's a reason we can, it is not the SI unit for temperature. But I want to show you something. Between freezing and boiling, we have 100 degrees. No matter, every time we go up, we change 1 degree, it represents a certain amount of kinetic energy change on that. But on the Fahrenheit scale, there's 180 degrees difference between freezing and things. Now, each one of those degrees also represents a certain amount of kinetic energy change. But if I changed 1 degree Celsius and 1 degree Fahrenheit, which represents a greater change in energy? A change of 1 degree Celsius or a change of 1 degree Fahrenheit? Celsius, right? Because there are fewer degrees. In fact, almost a change of 1 degree Celsius is almost twice as much energy change. It's 1.8 on that, which would actually give you a more accurate thermometer, a more finely graded thermometer. Fahrenheit, because you have a few more marks and things like that. So you can see between these two scales that although they both are measuring kinetic energy, are they measuring the same amount of kinetic energy? No. In fact, when temperature changes in Celsius, Celsius represents a greater change in temperature. When you change temperature in Celsius, represents greater change of that. Also, just as a little factoid kind of thing, 1 over 180 actually has a name. It's called a Farad. Farad. Cute nice little factoid things. But 1/180th of something is a Farad. It's an engineering thing. I have no idea what they use it for, but I know it comes from engineering on that. So questions about Celsius and Fahrenheit. Again, not our unit. We need more time? Leads us to Kelvin. Kelvin scale. Notice we don't say degrees